Negative mass and its weird implications for reality. Imagine a world where everything you know about mass and movement gets flipped upside down. Imagine pushing an object, but instead of it moving away from you, it moves toward you. This is the bizarre reality of negative mass, a concept in theoretical physics that challenges the way we understand the universe and forces us to question the very laws of nature. Negative mass isn't just an obscure theory. It opens a Pandora's box of weird and mind-bending possibilities that could change our understanding of reality itself. What is negative mass? To understand negative mass, let's start with what we know: positive mass. In physics, mass represents the amount of matter in an object and determines how it responds to forces. Newton's second law tells us that if you apply a force to an object with mass, it accelerates in the direction of that force. This simple principle forms the basis for much of what we observe in the physical world. Push a ball, and it rolls forward. Pull a chair, and it comes toward you. But what if the object had negative mass? In this scenario, the rules change dramatically. If you apply a force to an object with negative mass, it accelerates in the opposite direction. Imagine pushing a negative mass object away from you, and instead of moving away, it zooms toward you, almost as if it's deliberately defying your expectations. This isn't just theoretical fun. It has real implications that challenge our understanding of the laws of physics. Runaway motion, a strange phenomenon. One of the strangest implications of negative mass is something called runaway motion. Consider what would happen if you put a positive mass object near a negative mass object. The positive mass is attracted to the negative mass, and the negative mass is repelled by the positive mass. This leads to an endless chase, with both objects accelerating together in the same direction, seemingly gaining energy without an external source. This process could theoretically go on forever, violating our current understanding of energy conservation and stability in physical systems. Runaway motion is a paradox because it implies that there's no resistance, no energy loss, and no end. If such behavior were possible in the real world, it would redefine how we think about forces and energy, creating a universe where limitless acceleration is possible under the right conditions. The role of negative mass in theoretical physics. Negative mass is not just a curious idea with no practical value. In fact, it plays a significant role in some of the most speculative theories in modern physics. The concept of negative mass is often linked with the idea of exotic matter, a hypothetical form of matter that defies the norms of positive mass. Exotic matter is theorized to be essential for phenomena like wormholes and warp drives. Warp drives. In the 1990s, physicist Miguel Alcubierre proposed a theoretical model for faster-than-light travel, famously known as the Alcubierre warp drive. This concept relies on manipulating space-time itself to create a warp bubble, a contraction of space in front of a spacecraft and an expansion behind it. To do this, the warp drive requires a type of negative energy, which could theoretically be provided by negative mass. The negative energy density would allow space-time to bend in unusual ways, creating shortcuts across vast distances in the universe. While this concept is purely speculative at this stage, the idea that negative mass could facilitate faster-than-light travel is a tantalizing glimpse of what could be possible in the distant future. Wormholes. In a similar vein, negative mass is also theorized to play a role in stabilizing wormholes. Wormholes are like tunnels through space-time that could potentially connect distant parts of the universe, providing a shortcut for travel. However, most solutions in general relativity suggest that wormholes are inherently unstable and would collapse almost instantly. Negative mass could act as a stabilizing force, preventing the collapse and keeping the wormhole open, thereby allowing traversable paths between distant regions of the universe. Does negative mass exist? The big question, of course, is whether negative mass actually exists. So far, there has been no direct evidence for naturally occurring negative mass in the universe. However, certain physical systems exhibit behaviors that resemble negative mass. For example, in 2017, researchers at Washington State University created a peculiar fluid with properties that acted like it had negative mass. When the fluid was pushed, instead of moving in the direction of the force, parts of it accelerated backward, just like a negative mass object would. While this doesn't mean we've found negative mass in a conventional sense, it shows that under very specific conditions, the universe can exhibit behaviors that mirror what negative mass would theoretically do. Could negative mass explain dark matter or dark energy? Some scientists have even speculated that negative mass could be related to dark matter or dark energy. Dark matter makes up about 27% of the universe and is responsible for the extra gravitational effects that hold galaxies together. It's invisible and doesn't interact with electromagnetic forces like regular matter. Since negative mass could have gravitational effects opposite to those of positive mass, it's been proposed as a candidate for explaining some of these mysterious cosmic forces. On the other hand, dark energy is the force driving the accelerated expansion of the universe. Negative mass, with its tendency to repel and behave oppositely to regular matter, could theoretically contribute to this effect. Although these ideas are purely speculative and haven't been confirmed, they highlight just how little we know about the universe and how negative mass could be the missing piece in our cosmic puzzle. Violations of fundamental laws. Negative mass presents serious challenges to some of the most basic principles in physics, like the conservation of energy. The idea that a positive and negative mass pair could accelerate indefinitely without an external energy source suggests a potential violation of energy conservation. This goes against the grain of what physicists believe to be true about how energy works. Such scenarios raise fundamental questions. Are our laws of physics incomplete? Could there be hidden factors or mechanisms at play that we have yet to discover? A universe full of paradoxes, the concept of negative mass challenges the symmetry and simplicity of our universe. If negative mass does exist, why have we never seen it? Is it because it exists in such a way that it remains hidden from us, or could it be interacting with the universe on a scale that we haven't yet comprehended? These questions push the boundaries of our understanding of space, time, and matter, suggesting that there could be aspects of reality that are far stranger than we could ever imagine. Negative mass, though entirely hypothetical at this point, gives us a unique window into how much we still don't understand about the universe. It forces us to rethink the laws of motion, gravity, and energy. It invites us to explore ideas like wormholes and warp drives and to consider whether there are entire categories of matter and energy that we haven't yet discovered. Whether or not negative mass is real, the implications of its existence are so profound that they remind us just how strange, mysterious, and exciting the universe truly is. Call to action. If you're intrigued by the mysteries of the universe, don't stop here. Dive deeper into the world of theoretical physics. Like, share, and subscribe for more mind-bending content.
Imagine peering into the very fabric of our universe, zooming in past atoms, protons, and quarks. Eventually, you would reach a point where our conventional understanding of space and time begins to break down. At this unfathomably small scale, something extraordinary happens. Space-time itself becomes a dynamic, frothy sea of constant fluctuations. This phenomenon is what physicists refer to as space-time foam or quantum foam, and it reveals the bizarre and unpredictable nature of reality at its most fundamental level. The concept of space-time foam was first proposed by physicist John Wheeler in 1955. Wheeler, known for his pioneering work in quantum mechanics and general relativity, envisioned the universe not as a serene, continuous backdrop, but as a stormy, restless fabric when observed at the tiniest scales. To understand this idea, we need to journey into the realm of the Planck scale, where distances are as small as 1.6 x 10 to the 3 meters. Here, space-time is far from smooth. It is restless, agitated, and constantly changing, almost like the bubbles that form in a pot of boiling water. At the Planck scale, the known rules of physics start to disintegrate, giving way to the bizarre effects of quantum mechanics. The uncertainty principle, a cornerstone of quantum theory, dictates that energy fluctuations at such small scales are inevitable. These fluctuations, in turn, lead to the spontaneous creation and annihilation of virtual particle-antiparticle pairs. These ephemeral events cause space-time to warp and twist, giving it a chaotic, foam-like quality. This is where space-time ceases to be a calm and predictable fabric and instead becomes a bubbling, fluctuating quantum sea. To understand what Wheeler meant by quantum foam, it's helpful to think of space and time as something dynamic rather than static. At our everyday scale, space-time appears smooth, like the surface of a calm ocean when viewed from far away, with only gentle ripples and minor fluctuations. But just as an ocean hides turbulent currents beneath, space-time hides its restless, dynamic nature at smaller scales. In the case of space-time foam, we are zooming in to a scale where space and time are anything but calm. Instead, they are writhing with relentless activity. At this level, fleeting fluctuations in energy are so intense that they cause the very geometry of space-time to continuously shift. The constant interplay of energy creates tiny bubbles, warps and curves, as if space-time itself is foaming. Virtual particles pop into and out of existence, stretching and bending space-time before vanishing again, in accordance with quantum laws. The result is a picture of space-time that is anything but fixed. It's more like a frothing, ever-changing sea of possibilities. One of the most intriguing questions about quantum foam is whether it actually exists. Experimental evidence for quantum foam remains a challenging puzzle. Some experiments, like those observing the Casimir effect, provide indirect support. The Casimir effect, which measures the force between two uncharged metal plates in a vacuum, can be explained by the influence of virtual particles, hinting at the restless nature of space-time. These experiments suggest that the vacuum of space is not truly empty, but rather filled with transient activity. Physicists have also looked at gamma-ray photons arriving from distant cosmic events, trying to detect whether the predicted foaminess of space-time causes a slight variance in the speed of light as it travels over astronomical distances. Such variations could serve as evidence of space-time's quantum structure, but so far results have been inconclusive. The technology required to observe quantum foam directly is beyond our current capabilities, but the tantalizing prospect drives ongoing research and theoretical exploration. The idea of space-time foam has profound implications for our understanding of the universe. It suggests that at its most fundamental level, reality is in constant flux, a sharp contrast to the classical picture of a smooth and predictable cosmos that has dominated physics since Newton. Quantum foam represents a key aspect of the problem of reconciling quantum mechanics with general relativity, Einstein's theory that describes gravity and the curvature of space-time. If space-time is foamy at the smallest scales, then the unification of quantum mechanics and general relativity must involve understanding this turbulent fabric. This quest for a unified theory, often referred to as quantum gravity, remains one of the greatest challenges in modern physics. Approaches like string theory and loop quantum gravity are attempting to explain how these two pillars of physics can coexist, and the nature of space-time foam plays an essential role in these pursuits. In summary, space-time foam reveals a dynamic and unpredictable universe, challenging our understanding of reality and pushing the boundaries of what we think we know. It portrays space-time as something dynamic, turbulent, and filled with possibilities, constantly influenced by the unpredictable dance of quantum fluctuations. Wheeler's vision of space-time as a frothy, restless entity challenges our classical intuitions and suggests a universe where certainty gives way to probabilities, and the solid ground beneath our feet is anything but stable at the smallest scales. While we may not yet have direct evidence of space-time foam, the concept captures our imagination and underscores the notion that, at the deepest level, the universe is filled with mystery and wonder. As technology advances and our theories evolve, we may one day be able to peer directly into this seething quantum fabric, unveiling the true nature of the cosmos and our place within it. To explore more about the mysterious and awe-inspiring universe, subscribe to our channel and join the conversation in the comments below.
What if gravity, one of the fundamental forces that shapes our universe, wasn't fundamental at all, but instead emerged from deeper principles rather than being an intrinsic property of nature? This is the central idea behind emergent gravity, a theory that challenges what we thought we knew about how the universe works. The concept behind emergent gravity. Emergent gravity suggests that gravity might not be a primary force like electromagnetism. Instead, It could be a phenomenon that emerges from the collective behavior of microscopic components, similar to how temperature emerges from the average energy of molecules in a gas. Think of it like the behavior of crowds at a concert. Each person acts individually, but their collective movement forms larger, emergent patterns. In this view, gravity isn't a force in the traditional sense, but an emergent property of the underlying structure of space and time. Dutch physicist Erik Verlinde introduced a new perspective on gravity in 2010, drawing inspiration from quantum mechanics and thermodynamics. Verlinde proposed that gravity is akin to entropy, the tendency for systems to move towards equilibrium. In his model, masses distort an entropy landscape, a conceptual representation of how disorder changes in the presence of mass. And the tendency of the universe to maximize entropy creates the gravitational attraction we observe. Gravity may be an illusion in the sense that it emerges from the interaction of more fundamental components, rather than being a standalone force. It's like how surface tension is not an independent force, but the result of interactions between water molecules. Similarly, gravity might be the macroscopic result of many small interactions happening at a microscopic level. The holographic principle and gravity. A key element of emergent gravity is the holographic principle, which suggests that all the information contained within a volume of space can be described by information encoded on its boundary, like a hologram. Imagine a can of soup. All the information about the soup's contents could, in theory, be represented by information on the label. Similarly, the three-dimensional space we perceive might be encoded on a two-dimensional boundary. This means that what we perceive as three-dimensional space could be a projection from a deeper, underlying reality. In emergent gravity, gravity arises from information encoded on the boundaries of space. The presence of mass and energy alters this information, leading to the emergence of gravity. Imagine a black hole. All the information about what falls into it is encoded on its event horizon. Emergent gravity extends this idea to the entire universe, suggesting that gravity is an emergent feature of how information is organized. Implications and challenges. If gravity is emergent, it could change our understanding of the universe and provide an alternative explanation to dark matter. Traditionally, dark matter is invoked to explain why galaxies rotate at speeds that, according to visible matter, should not be possible, implying the existence of unseen mass providing additional gravitational pull. To connect emergent gravity with dark matter, consider that instead of invoking invisible matter to explain galactic motion, Verlinde suggests that the way gravity emerges at large scales could account for observed discrepancies. This means that the extra gravitational pull observed in galaxies might be explained without dark matter. However, emergent gravity is still a hypothesis. General relativity, Einstein's theory of gravity, has stood the test of time in numerous experiments. Any new theory must replicate these successes and provide new predictions that can be verified. So far, emergent gravity hasn't reached the level of detail and predictive power needed to replace general relativity. Is gravity just an illusion? So, is gravity just an illusion? In the context of emergent gravity, it might be. Not an illusion in the sense that it's not real, we still feel its effects, but an illusion in the sense that it's not fundamental. Instead, gravity could be a byproduct of deeper processes involving space, time, and information. This perspective opens up fascinating possibilities. It hints that our understanding of the universe is still in its infancy, and there could be deeper layers of reality waiting to be uncovered. Perhaps gravity, dark matter, and even space-time itself are all emergent phenomena. It challenges us to question what is fundamental and what might be a complex illusion brought about by underlying processes. While emergent gravity is still developing, it captures the imagination. It reminds us that even the forces we take for granted might be hiding secrets, and the universe is far stranger than we can imagine. Our journey to understand the cosmos is far from over, and emergent gravity remains a hypothesis that encourages us to explore further, questioning what we know and searching for deeper truths about the nature of reality. What other fundamental forces or phenomena might also be emergent, waiting for us to discover their true nature?
Imagine waking up one day and realizing that everything you know, the stars, planets, your memories, even your body, is just an illusion, a fleeting moment in a vast, random universe. This idea may sound strange, but it's at the core of the Boltzmann brain hypothesis, which challenges our understanding of existence and consciousness. The origin of the Boltzmann brain hypothesis. The Boltzmann brain hypothesis is named after Ludwig Boltzmann, a 19th-century physicist who studied entropy and randomness in physical systems. Boltzmann suggested that, given enough time, random fluctuations could cause temporary reductions in entropy, allowing order to emerge out of chaos, if only briefly. This concept helps explain how stars, galaxies, and complex systems can form in an otherwise disorderly universe. But what if these random fluctuations produced a conscious brain with thoughts, memories, and a sense of self? The birth of a disembodied consciousness. This disembodied consciousness, spontaneously created by random events, is what we call a Boltzmann brain. The concept is significant because it challenges our understanding of reality, suggesting that consciousness might arise in ways we can't easily predict or comprehend. If the universe is infinite and time stretches on forever, it becomes statistically inevitable that atoms will randomly assemble into anything imaginable, even a conscious mind floating in space, with a full set of memories and experiences. This leads us to an unsettling question: could we be Boltzmann brains? Could our entire existence be nothing more than a random fluctuation, a fleeting blip in an otherwise empty and chaotic universe? Are we really just Boltzmann brains? The unsettling part of the Boltzmann brain hypothesis is that, from a probabilistic standpoint, it might be more likely for a single brain to emerge by chance. This could mean that an entire universe evolving in an orderly way to produce billions of conscious beings like us is less probable. If that's true, then statistically speaking, it might be more probable that we are just disembodied consciousnesses than physical beings in a consistent, structured universe. This hypothesis raises the possibility that everything we perceive, our memories, our relationships, the world around us, could all be illusions. These illusions might be fabricated by a consciousness that randomly sprang into existence. It's a mind-boggling idea that has led to intense debates among physicists and philosophers, challenging the very foundations of how we understand reality. The counter-arguments, however, many scientists and philosophers, such as Sean Carroll and Alan Guth, argue against the Boltzmann brain scenario. They point out that if Boltzmann brains were more common than evolved beings like us, we would expect a very different kind of universe, one without the consistency, structure, and observable laws of physics that we experience. The fact that our universe appears comprehensible and orderly strongly suggests that we are not just random fluctuations. Moreover, the Boltzmann brain hypothesis is often seen as pointing to a paradox. If such disembodied brains were more probable, then why do we experience such a stable reality? The existence of consistent physical laws, galaxies, and life on Earth suggests that our universe is not a chaotic accident but has evolved in a structured and predictable way. What does it mean for us? While the Boltzmann brain hypothesis is intriguing, it's a thought experiment meant to push our understanding of entropy, probability, and consciousness. It doesn't mean that we should seriously consider ourselves as disembodied consciousness floating in a void. Instead, it reminds us of just how mysterious and vast the universe is, and how much we still have to learn about the nature of reality. The Boltzmann brain hypothesis makes us wonder, what exactly is consciousness? How can we be sure that what we experience is real? Can we ever truly understand our place in the universe? While we may not have definitive answers, contemplating these questions helps us appreciate the complexity of existence and the beauty of our orderly, structured universe, a place where, against all odds, we can look up at the stars and wonder about our own beginnings.
Imagine a universe-ending event that could occur without warning, faster than the blink of an eye. It's called vacuum decay, and while it sounds like something from a sci-fi thriller, it's actually a concept rooted in real physics. Let's dive into what vacuum decay is, how it could bring about the end of the universe, and why it's both terrifying and utterly fascinating. The quantum field and the false vacuum. To understand vacuum decay, we need to take a look at the concept of the vacuum in quantum field theory. Unlike the classical vacuum of space, which we think of as empty, the quantum vacuum is far from void. It's a state with the lowest possible energy level, filled with fluctuating energy and particles that continuously appear and disappear. But what if this vacuum we're familiar with isn't actually the true lowest energy state? Physicists believe there's a possibility that our universe exists in a false vacuum, like a marble resting in a shallow dip on a hill, appearing stable but not truly at the lowest point. If this false vacuum were to transition to the true vacuum, the consequences for the universe would be catastrophic. In a false vacuum, the energy level is not at the true minimum, which means it could potentially roll down to a lower energy state. This transition would release an enormous amount of energy, leading to drastic changes throughout the universe. The false vacuum might seem stable, but it's akin to being in a precarious balance. A small enough disturbance could be enough to tip it over into a new, vastly different state. The bubble of doom. If vacuum decay were to occur, it would begin with a quantum event, a tiny region of space where the false vacuum shifts to the true vacuum state. This would create a bubble of true vacuum, and this bubble would expand at nearly the speed of light. As it spread, it would fundamentally alter the physical properties of the universe, such as changing the masses of particles, altering the strength of fundamental forces, or even modifying the nature of atoms themselves. Inside this bubble, the laws of physics as we know them would change entirely. The particles, forces, and constants that govern reality could all be different, and the result would be complete annihilation of anything in its path. Essentially, it's a cosmic reset button that no one wants to press. This bubble of true vacuum would not only expand rapidly, but it would also erase everything in its path. Stars, planets, and entire galaxies would be swept away by the advancing wall of this new vacuum state. The expansion would be so swift that nothing could outrun it or resist it, as it would propagate at nearly the speed of light, leaving no chance for anything to escape. It's a sobering thought. The universe as we know it could be erased in an instant, replaced by something we can barely comprehend. Why would this happen? The stability of our universe is closely tied to the Higgs field, which gives particles their mass. The Higgs field is a quantum field that permeates all of space, and particles acquire mass by interacting with it. The energy level of the Higgs field could determine whether our universe is stable, metastable, in a false vacuum, or unstable. Current measurements hint that our universe might be metastable, meaning vacuum decay is theoretically possible. However, the likelihood of this happening seems incredibly low, especially within any time frame we'd have to worry about. One potential catalyst for vacuum decay could be a high-energy event that disturbs the false vacuum, causing it to collapse into the true vacuum. This could involve extremely high-energy cosmic rays or some hypothetical advanced technology. Fortunately, the conditions required for this are so extreme that we can safely consider them highly unlikely. Another possible trigger could be an event at the quantum level, where fluctuations cause a tiny region to fall into the true vacuum state. The idea of quantum tunneling comes into play here, an effect where particles can pass through energy barriers that would otherwise be insurmountable. In a similar way, the universe could suddenly tunnel from the false vacuum to the true vacuum, setting off a chain reaction that would expand uncontrollably. Instantaneous, unpredictable, and inescapable. One of the most unnerving aspects of vacuum decay is that it could happen at any moment, and we'd have no way of knowing it was coming. The bubble of true vacuum would expand at nearly the speed of light, leaving no time for warning or escape. One moment, everything is as it is. The next, reality itself has been rewritten. The inescapable nature of this event makes it a unique kind of existential threat. Unlike other cosmic dangers, like asteroids, supernovae, or even black holes, there is no way to detect or predict vacuum decay. Its onset would be completely random, and there would be no way to shield ourselves or prepare for it. The only consolation is that, if it were to happen, we wouldn't even have time to perceive it. It would be over before we could comprehend what was happening. But while this idea sounds chilling, it's important to remember that vacuum decay is highly speculative. The universe has been around for 13.8 billion years, and if we are indeed in a false vacuum, it has remained stable for all this time. The timescale for such an event is thought to be far longer than the current age of the universe, likely trillions upon trillions of years in the future, a thought experiment to keep us humble. Vacuum decay remains a captivating thought experiment, a reminder of just how mysterious and delicate our universe is. It highlights the gaps in our understanding of fundamental physics and keeps us humbled by the cosmic forces at play. In the grand scheme of things, it's one of those ideas that makes us appreciate both the beauty and fragility of existence. This concept also serves as a reminder of how much we have yet to learn about the underlying nature of reality. The universe operates on scales and energies that are far beyond our everyday experience, and concepts like vacuum decay push the boundaries of what we can understand. It makes us ask deep questions about the nature of stability, existence, and what might ultimately bring about the end of everything we know. So while the end of everything in an instant is a terrifying possibility, it's not something to lose sleep over. Instead, it's an invitation to marvel at the mysteries of the cosmos and our tiny place within it. The universe is vast and filled with wonders, and the fact that we can even ponder such possibilities is a testament to our curiosity and desire to understand the world around us. Ultimately, vacuum decay is a humbling reminder of our place in the cosmos. We are small, fragile beings living on a tiny planet in a universe that is both incredibly beautiful and deeply enigmatic. Yet, rather than fear the unknown, we can choose to embrace it with curiosity and wonder. Let this be a call to action, to explore, to learn, and to marvel at the mysteries of the cosmos, using our knowledge to deepen our understanding and appreciation of the incredible universe we inhabit.